Hello. In this video, we will go over an introduction to differential equations, and we will also discuss direction fields. I apologize for my handwriting. It is difficult to go through and write clearly using a writing tablet. Okay, so first, what is a differential equation? So let's come up with a simple definition that will work, that will suffice. A differential equation is an equation containing derivatives. To be more explicit, it's an equation containing derivatives where you go through and you solve for the function that you'd plug into the equation that would make the equation true. Okay, so we'll make this clear in the sections to come, and I'll repeat that again. But a differential equation is an equation that contains derivatives of a function where the solution of the equation is a function. It's the function that you'd plug in, where you'd go through and take the derivative, and you'd end up getting a true statement when you plugged in that function. So the solution is a function as opposed to being a number. Okay, so why study derivatives? Since a derivative can be used to represent a rate, problems in the natural world that involve rates can be solved with differential equations. What are we talking about? So what type of problems in the natural world involve rates? Well, motion of objects, so like falling bodies, which is an example that we're going to look at in a second. Other examples, motions of fluids. Motion of fluids involves rates. Other examples, flow of current in electrical circuits. Okay, what else? Dissipation of heat. In solid objects. Proposition / detection of seismic waves. So all of these things have rates. and population. So we are not going to get into all of these applications in this class, but we're going to get into some of them. We'll look at dissipation of heat. We'll look at motion of objects in this section. We'll look at population growth. We'll look at flow of current. Maybe everything, but well, even the seismic waves. Maybe we do get into that a little bit, but we get into most. We're going to get into most of these. Okay, so let's go ahead and get into one of them right off the bat. So first thing that we're going to do is we're going to add one more definition here, and that is a differential equation that describes a physical process is called a mathematical model. All right, so we have a whole bunch of definitions here. So we've got a definition for a mathematical model, definition for differential equation, and then some examples. Okay, so using that kind of as our starting point, what we're going to do is we're going to jump in so that we can actually look at some differential equations by going through and doing some math models. All right, so that's the next step. Let's get to that. All right, so our first example of a mathematical model So the first one we're going to look at is the falling object problem. Okay, so to go through and model a falling object, we start with Newton's second law. Which states F equals ma, where F in this case is the net force acting on an object. A is the mass. M is the mass, sorry. A is the acceleration. Okay, and since we're going through and modeling the motion of an object, we can go through and we can say that A equals dv dt, right? So our object is going to change velocities over time, and so the A is not going to be constant, so we can go through and replace the A with dv dt. So when we put those together, we get F equals m times dv dt. Okay, and then next, we look at the individual forces that would apply to a falling object. So one force that acts on a falling object is the force due to gravity. So we'll call that F with a little sub g, and that is the mass times the gravity. And the other force, another force that would, so that the gravitational force would pull the object downward, and then acting opposite that, we would have an air resistance or a drag force. Okay. And we'll represent that with a little d. And so that's going to be a drag constant times the velocity. So with the drag force, the faster you're going, the larger the drag force is going to become. So it acts proportional to velocity. Okay. And when we put those two together, so those two act in opposite directions, right? So the gravitational force pulls us downward, and the drag force pulls it upward. So if you were to do a force diagram, you'd have FD acting one way and FG acting the other. And so because of that, we're going to give them opposite signs, and we can go over to here and say that our net force, right, is going to be the combination of these two. So that's going to replace F. So if you do that, you'll have M dV dt, right? That's F equals MA, which equals M dV dt. And then that equals the net force, which is the capital F there. And that's going to be mg minus gamma v. And then if you go through and divide through by m, we end up getting dV dt equals g minus gamma over m times v. Okay, so I realize there are a lot of letters there, so it can be a little bit difficult to see, but these are, a lot of these letters are constants, right? So the G is the gravitational constant, so that's going to be 9.8, assuming you're using meters. The mass is going to be a constant, right? The object's not going to change mass as it's falling, so that's going to be a constant. This the drag constant, given by gamma, that does not change either. So this is a constant, this is a constant, and this is a constant. And if you go through and just plug those numbers in, what you're going to find is that you're going to have a dV dt and v are going to be the only variables that you're going to have up there. And what this is saying is the derivative of velocity ends up equaling some equation that contains velocity in it. And that's a classic differential equation where we have an equation that has a derivative and the original function in it. Okay, so the last thing that we can do is you can go through, and this will model any type of falling object that, this is a simple falling object structure here, but any object will model this. To go through and actually have specific models, you're going to go through and you'll plug in a mass and a velocity. All right, so to model a specific situation, plug in mass and the drag constant. So for example, if the mass equals 5 and the drag constant equals 1, then we end up with dV dt equals 9.8, right? Just plug in g as well, minus 1/5 v. All right, so now we've got our differential equation. an equation that contains a derivative and the original function. So if we were to go through and solve this, which we're not going to do in this section, but we'll do it in the next section. If we were to go through and solve this, what we'll end up with is we'll end up a function that we could plug in, where if you put the function here and you put the derivative of the function here, it will make the equation true. Okay. So we'll go through and study this in a few minutes. Now we're not going to solve it, but we could study it. We'll study it in a few minutes. But for now, what we want to do is we want to go through and come up with a second model so that we have two to work with. All right, so the second model that we're going to look at is a model for population growth of mice and owls. So in this case, we start off with the basic idea that populations that are unrestricted grow proportional to the existing population. Okay, so to go through and represent that, what we start off with is dp dt equals r times p. Okay, so this is the growth of the population. This is the growth rate. And this is the current population. So again, the idea here is that if you have a large population, then the growth of a large population is going to be large. If you have a small population, then the growth of a small population is going to be small. So populations grow at a rate that is proportional. This is like a proportionality constant times the current population. Okay, so that's going to represent that could represent the growth of our mice, and then we're going to add a component for owls. Okay, and so the way to handle that is you're just going to subtract that value off, right? So dp dt equals rp. This is going to give us the number of new mice that we would get over a time period, say a month. And then to figure out what the growth would actually be, we're going to take the number of new mice and we're going to subtract off the number of mice that the owls eat. And then the rest, what's left, is going to be the number of new mice. It's going to be the growth in the mice. Okay, and so that gives us a model for populations of mice and owls. So to go through and model a specific situation, we could substitute for R and K. So those are the two things that would change for different situations. So R could be the rate of growth of the mice. So maybe one type of population of mice grows at one rate, and a different type of mice grows at a different rate. So some mice maybe procreate faster or slower than others. And K would be the number of owls that are eaten. So that value could depend upon how many owls there are. If you have more owls, then you get a larger K value. Yeah, so just specifically, so if we said if R equals 0.5, so that's the growth rate. And so you could think of that as a percentage. That's a 50% growth rate over our time period, which we're saying is a month. And K equals 450. So that's assuming 450 mice are eaten by owls per month. Then we get dPdt equals 0.5 p minus 450. So that gives us a second equation that we can go through and study, okay, to see its characteristics. Okay, so we're not going to solve these, but we're going to study them. We'll solve them in the next section. Okay, so how do we go through and study these? What tools can we use to try and interpret some information in these two cases? So the next thing we want to do is we want to go through and study the modeled equations that we've generated. So to go through and do that, what we're going to do is we're going to use direction fields. So the idea behind a direction field is a little bit similar to a vector field in that we have a two-dimensional image, and that image has a bunch of arrow type things on it. And by looking at those, we can interpret how the underlying object behaves. Okay, so let's just write that down. A direction field contains the plot of slopes on a coordinate axis. You can go through and you can generate a direction field by hand. To do that, what you want to do is you want to go through and you want to plug inputs into your equation. So for example, let's say we had dy dt, and it equals 4 minus 2y. All right, so this is a differential equation just like the previous ones that we've been looking at. And what we can do is we can go through and we can plug in points into this and then go through and graph those points on a coordinate axis, right? So let's just throw a coordinate axis over here that we can use for plotting on. Okay, and so to do that, you could just say dy dt, and then you're just going to pick a point on here and plug it in. So you could say plug in 0. And so what I'm going to do is I'm not just going to plug in 0. So since there's no t in the equation here, I'm going to say, let's just leave t generic. So I plug in t comma 0 for any t value. I'm going to end up getting 4 minus 2 times 0. So I'm going to end up getting 4. So what this tells us is this tells us that for all t values, that have a coordinate of 0 for y, we're going to end up getting a slope of 4. And so what we're going to do is we're going to draw slopes of 4. Okay, and so what we've done is we've generated part of the direction field. And so we can go through and generate more of it by picking something else to plug in. So we could say plug in any point that has the first coordinate comma 1. And if you do that, you're going to end up getting 4 minus 2, which is going to be 2. So that's going to give us a shallower slope at 1. So at 1, we're going to get a shallower slope. And then we could go through and we could plug in t comma 2. And if we do that, you're going to get 4 minus 4. So that would be 0. So at 2, so this is 0, 1, 2, we're going to get a 0 slope. And so you can see we could go through and you can generate a direction field by hand. However, that's not typically how we go through and do it. Direction fields are normally generated using a graphing utility. All right, so normally you don't do it this way. You can do it this way, but normally you use a graphing utility. Okay, so let's go ahead and switch over to a graphing utility. All right, so we want to get a direction field plotter. So to do that, what you want to do is go to your Google prompt and just type in direction field plotter. Okay, and you can go through and use whichever one you want, but I'll show you the Geodrabo one, which I think is pretty good. All right, so we start off. Let's pick one of the equations that we said we were going to study to plug in here. So the first one that we did was 9.8 minus 0.2, right, 1/5 times, and then so the variable we're using here is that we're using x and y instead of t and v, but the y is in place of the v, so you want to put y in there. Okay, so this is going to happen frequently when you go through and use a direction field plotter. And what this is showing is it's showing us that the interesting information on this function is not visible. It's not focused right now on the screen. So what we need to do is you need to go through and change the focus here. So instead of going from -5 to 5 for x and y, we need to pick, make a better choice in terms of what we're looking at. So I'll explain in a minute why I'm going to make this choice, but it's just going to simplify things a bit if we go, say, from 0, so no negative time, to 20. Okay. And then on top of that, I'm going to change the y values. And again, I'll explain where this comes from in a minute. We're going to change them to 45 to 55. Okay. So now the focus here is from 0, 20, 45 to 55. And so you can see you don't see any arrows here. So what you need to do is you need to just zoom out. And you see here, there's the arrows. All right. So if you just go through and get those centered and then zoom back in, you can see, congratulations, you've got your direction field. Now you've got some options here. You can go through and change the length. So we can make these a little bit longer. All right. And so this gives us a set of slopes for the function. Okay, so the thing that makes this really enormously valuable, and it may not be something that is immediately recognizable, is the fact that the slopes here, those are the slopes that actually fit onto the curves that are the solution to the differential equation. Okay, so if you were to go through and say, all right, so let's say that we have a solution and it has a slope here. That means if I were to draw a curve, right, along, near this point, this would be the tangent line. This guy right here would be the tangent line. Let's make them even a little bit longer. So that would be the tangent line. Okay, and if you think about a curve and this is the tangent line, then that's kind of pointing us in the direction that the curve would go, right? So if you think about a curve where this is the tangent line, then the curve is moving this direction. Okay, and if you just kind of follow along the path that this points in, eventually you hit another curve or another area where there's curves, and you can see that the curves become more shallow. So you could kind of think about this, that this points us this way, then we get over here, and then that points us to being more shallow, and then that points us to being more shallow, and yet more shallow. And you could go through and you can kind of trace out a curve by using the slopes, okay, that are on here. And so that's the neat thing about direction fields, is that they can actually help us visualize the solutions by drawing curves that fit onto the slopes. And you can do the same thing down here below. So if you started, say, at this point, you could say, all right, well, if this is going to be tangent to the curve, then this is the direction that the curve is heading until you get to here, and then it becomes shallower, until you get to here, and then it becomes shallower, and until you get to here, it becomes yet shallower. And so you could kind of trace along curves that fit onto the slopes and to go through and generate things that actually solve the differential equation. Now, you can actually graph those things on this curve by using these solution options. All right, so these solution options are actually using the technique that we just talked about. So we're going to get into this in a few, toward the end of this chapter, a method called Euler's method for going through and graphing solutions to differential equations. And what it does is it actually uses a slope, and it says, I'm going to use this slope here. I'm going to put a curve onto that, and I'm going to start there, move along. Then once I get to this spot, I'm going to recalculate with a different slope, recalculate with a different slope. And that's what this step size is. The step size is how far you go before you recalculate. So 0.1 is a relatively small value, and you'll be able to see in a second when we actually put some curves on here that they do a good job fitting onto these slopes. All right, so let's go ahead and initiate two different curves. Now, the only thing that's a little bit problematic is that those curves are not, they're located down here where we started. So let's go ahead and drag those up. Okay, and then we can zoom back in. And so what we can see is we can see some different behavior for the function that would solve the differential equation based upon the starting point. So if we started at 54 velocity, then the velocity slowly decreases until it approaches some value. And if we started with 46 for the velocity, it slowly increases. So if we start with a high velocity, it decreases. And if we start with a low velocity, it increases. And no matter what, the velocity eventually approaches a value here that's in the middle. And we can go through and change this, still approaches the same value, still approaches the same value. No matter what we do, our object approaches the same value. All right, so that value has a I don't know if famous is the right word for it, but it has an important name. It's called the terminal velocity. Okay, so the terminal velocity is the fastest that the object can fall. If you start off falling faster than that, then you fall slower until you get to that value. And if you start off falling slower than that, you fall faster until you get there. Okay. Now, one of the things you may notice about this is if you went through and just kind of slid this along, you can end up getting a horizontal line that fits right onto the terminal velocity. So that's something that we're going to go through and note. That line, that horizontal line has an important name. Okay, it's called the equilibrium solution. So let's just jump back over to the whiteboard here for a second. All right, so the equilibrium solution. Okay, and that's going to be the solution where you get the horizontal line. Meaning it has zero slope. So we can go through and solve for that. So we can go through and solve for the place where the solution has zero slope by setting the derivative equal to zero, right? So what did we start off with? We start with dv dt equals 9.8 minus 1/5 v. If you go through and set dv dt equal to 0, you get 9.8 minus 1/5 v, and then 1/5 v equals 9.8, and then v equals 49. Okay, so earlier I said that if you start off with your graphing utility and it just gives you a bunch of lines that are kind of just pointing off the page, and you're trying to figure out, wow, where do I zoom in? One of the things that can help you is you could go through and you could try solving for the equilibrium solution. So if you had solved for the equilibrium solution first, like I just did, then you would have known, hey, I should zoom in around v equals 49. Okay, so let's go ahead and look at our other problem, and we can do that in advance. All right, so for our other problem, we had dp dt equals 0.5 p minus 450. So what would the equilibrium solution be here? Well, to figure that out, we could do dp dt equals 0. And then we'll get 450 equals 0.5 p, and then p equals 900. So this tells us that we should look to zoom in around 900. Okay, so now let's go through and switch back over. Okay, and then we can go ahead and plug that in. So we've got 0.5, and then we're using y for the variable, minus 450. And immediately you can see that things kind of turn into a mess in the picture. And that's because we need to zoom in around 900. All right, so let's go ahead and change this to 880 to 920. And now it's just completely off the page. So what we need to do is just zoom out. All right, so we're going to want these 2 points. So let's just drag them upward. I guess we should zoom out more before we drag them upward. All right, so that little patch of black is where the curve is. All right, so now let's zoom in there. That's around 900. All right, let's take a look. Let's put our 2 points on here. All right, so what is this? So let's just try and analyze this for a second. What does this tell us? Okay, so we can see from our direction field plot here that we have the equilibrium solution is right here in the middle. That's the amount, that's the number of mice where we would end up getting a slope of 0, a rate of change of 0. So what that would mean is that would mean that the number of mice doesn't change. So if you have 900 mice to start with, then the rate of change, the dp dt of the mice, is 0, meaning that you stay at 900. So if you were to interpret that, if you were to think about that and someone were to ask you to interpret that, what would you say? Well, what you could say is that 900 mice is the amount of mice that you'd need to have so that you would create enough mice to offset the loss of mice from the owls. So that's the number of mice that you'd have to have so that you have a large enough population, so that the population produces enough mice so that you can offset the number that the owls eat. All right, so if you have more than 900 mice, then you have enough to exceed the amount of mice that the owls are eating, and the population of mice grows over time. Meanwhile, if you have less than 900 mice, then you don't have enough mice to offset the number that the owls eat, and so the mice decline over time. And so that's how you could go through and interpret this graph. Okay, so that covers our first section. So we went through and we introduced the idea of differential equations. We talked about what you could use them for. We looked at a couple simple mathematical models. And we went through and discussed direction fields and how you could go through and study the solutions to those mathematical models. And that was it. All right, so I'll see you next time. Thank you very much for watching.